All right, let's get started here. So, a couple things before we kind of get going. Excuse me. What's due by the end of the day tomorrow? Quiz. Yeah, hopefully you've done it by now with that third quiz. That problem set is due before we start class on Tuesday, so I get this fall break. So hopefully you started on this early, got it done. If not, I will be here during my office hours on Monday. If you do tend to, or if you do plan to be around. I will also probably be around campus most of tomorrow, so if there's a time that works, shoot me an email. We'll probably meet to go over that last minute questions you have there. Otherwise, I will get the first problem set should be created for every single person, even kind of worse issues with do files. So I'm going to get the solutions up to that. That didn't help too much in studying for the exam, but as soon as that second problem set gets graded, I'll post the solutions to that. And then I'll also, after class on Tuesday, post the solutions to the third problem set. Now, not all of it's going to be that helpful for the exam because a lot of it's in Stata, but some of the questions that were more open-ended might be some good additional review. You'll have all the old practice problems. You'll have all the old quizzes. You can kind of go back through and look at those, rework those questions, especially the ones you got wrong. We have this midterm practice set of problems. So I'll probably work through a lot more of those on Tuesday, but if there's any questions specifically over those, we can start with those today. So that's kind of a roadmap where we're going. So what's a week from today? The exam. So I'm getting somewhat alarmed by the attendance, and we'll see. I just want something I can point to, maybe plausible, not plausible deniability, but I'm telling you that there will likely be no curve. There will likely be no retakes. There will, I say likely, there will not be, right? There will not be any kind of retake, any type of curve. And so, you know, I can't stress enough attendance in this class. It's going to be highly correlated with your performance on those exams. The exams carry a pretty high weight, right? So take this exam seriously when you're studying for it. Next week, Wednesday office hours, I imagine will be pretty important. So I'll probably tell I teach two big sections of B251. So I'll probably tell them, you know, if you have questions Wednesday, maybe I'll kind of move those office hours for them to next Friday so that it gives you guys kind of make sure I have priority for you guys on next Wednesday. Okay. Other than that, any questions for me before we get started? So I've got this additional life expectancy data set we'll kind of work with a lot today. And I'll kind of jump into it and kind of work through some what I think would be good examples. So although we're doing a lot of the work in Stata, you know, you can kind of see from that practice exam and what I might do on the exam. When I say might do, I've written it so I have an idea. I might give you Stata output and then ask you questions kind of from that. So I'm not going to ask you to like necessarily code anything, but you need to know for the exam how to pull statistics out of Stata output, you know, based off of different types of questions, how to kind of use those results to make predictions, etc. So are there any questions that anybody had if they had a chance to look at this practice exam? I want to kind of make these class periods as useful for you as possible. But if there are any questions over this, we'll kind of start with that. Otherwise, I'll kind of just jump into this new data set and we'll kind of work through some questions that I've kind of come up with. Okay. So hopefully in Tuesday's class, I'm thinking there'll be a lot more questions on this. So we'll be working through a lot more of these problems. But just another example of seeing more of these things we've talked about work through. I've got a blank do file pulled open. That's not what I wanted. I'm going to then open up. So there's that life expectancy data. If you want to follow along, you can kind of download that off of Canvas, put it into your OneDrive. So I've got on my OneDrive, it's sitting right here. So I'm going to open up that life expectancy data set. Just to kind of be complete here, I'm going to copy and paste my code. Also, I thought it was out enough, but maybe I didn't. There we go. So I'm going to add this just in case I want to go back and use this. I'm going to start out with a very kind of simple, basic linear regression, which is I'm going to want to try to predict this life expectancy variable. And I'm going to try to do so using GDP. Right? So if I look at this actual data, I've got different countries, years, different measures of infant mortality, BMI. Here's GDP. Well, now notice GDP is actually stored as what the GDP is. It's not scaled at all. Okay. So if I run this regression, just kind of think about what we're doing here. What's going to be the sign? Sorry. What's going to be true about the size? I guess we can think about the sign as well on that GDP variable. So it's going to tell me the effect of a 1 unit change in that X variable on the predicted Y variable here. So what's a 1 unit change? GDP here is measured in US dollars, so it would just be one additional dollar. The predicted increase or decrease it would have on life expectancy. What do we think probably is true about the sign of the effect? Positive. What about the size? Having one more dollar for GDP, we think that's going to increase life expectancy a lot? No, it's a really small unit change. So if I run this regression, excuse me, sure enough, 1.3 e to the negative 12, which means 0.00000000001, right? Very, very small effect because it's the effect of $1. When we look at GDP, it's measured in billion. I mean, it's in the billions, right? So what's one thing that we could do is scale that variable and say, take the original GDP variable, and I want to make it now not in terms of just $1. When I'm looking at GDP, I mean, the US is in trillions, right? So let's think about something that's a little bit more reasonable. Let's do a $1 billion kind of unit. So we'll divide this by 1, 2, 3, 1, 2, 3, 1, 2, 3, 9 zeros, right? So I'm dividing this by a billion. So it's converting it now. The units will no longer be $1. Now my GDP reg, or this new GDP variable, is going to represent billions of dollars. So 1 would be 1 billion, 20 billion, so on and so forth. So if I run a regression where I now use this GDP reg variable, what's going to happen to the size of that coefficient on this new GDP variable I scale? It's now going to be the effect of a, not $1 increase, but $1 billion increase. So what do you think is going to be true about the size? Should be higher, right? So I can kind of go ahead, run this, see if that's the case. Let's see, get this all in one. There we go. Sure enough, right? I went from a really, really, really small coefficient to now it's 0.0013. Now notice it's the same value, 1.38. 138. It's just that I'm moving the decimal because I've scaled it, right? And now this is something that's a little bit more, manageable to work with instead of having to type in 11 zeros here every time I want to use that coefficient. Now, when I scaled the variable relative to before, have I changed the information that exists in that x variable? The relative size of every single value should be exactly the same. So the amount of explanatory power that variable has should have not changed at all. So my r squared, even when I scale variables, should still be the exact same. You can kind of also imagine if I'm thinking about calculating something like a test statistic that's using that slope coefficient and dividing it by the standard error. Well, if I've scaled both of these kind of like by a billion, it's going to cancel out. I should have the exact same statistical significance on my coefficients as I did before. So scaling the variable really shouldn't change anything except for the size of that coefficient. And inherently, it's also going to change the size of my standard error. Right? I'm kind of scaling both of those things. Whoops. There we go. So sure enough, my r squared before was 0.041, still 0.041. Test statistic on that GDP variable, still 11.07. So scaling our variables doesn't do anything to the statistical significance or explanatory power. It simply changes the size of that coefficient and standard error. Okay? It just kind of scales them up. Okay? Questions on that before we keep moving? Shouldn't be too bad. So, excuse me. So the next thing that we can think about is, let's say, well, let's make this easy. Let's copy and paste here. And let's say I want to add in a second variable. It's capitalized, is it? Yeah. So let's say I want to add in population. So what's going to be kind of one issue if I include this population, and I think we had a similar example earlier in the semester, is anytime I have more people, inherently, that's going to be increasing my GDP. So this isn't perfect multicollinearity, But we said sometimes two variables can have some imperfect multicollinearity. Right? So this might be the idea that if I'm looking at age and experience, well, anytime I'm 1 year older, I'm likely going to have also one more year of experience. Now, not everybody who's 30 has the same level of experience, right? Just like here, not every country that has the same population will have the same GDP, but any increase in that population would inherently increase GDP. It's a linear function of each other. So we said we might have some imperfect multicollinearity here. Now, what happens if I have imperfect multicollinearity? Remember what that does in my regression. We said it impacts the variable's standard errors. Right? So we said it's going to at least increase the standard error of one of our variables, possibly both. Okay? So I could think about my very two basic regressions. So let's just say I ran these two variables separately, right? A regression with this GDP and a regression with population. I then run one where I include both. What I'll see here is, so originally that standard error on GDP was 0.0012, 0.0012, 0.0012 for population. What's happened to both of these here? Well, now 0.001 almost 4 and 0.0014, they both went up. Now, not a lot, right? But that's because we have relatively small standard errors in this example. But if we have some imperfect multicollinearity going on, and we didn't talk about any tests for this, this would have to be something I tell you, assume that there's some imperfect multicollinearity in these variables. What could happen? Well, we know at least one of the variables' standard errors will go up, or potentially both of them. Right? So why is this a concern? We said if we have some imperfect multicollinearity, oh, come on. If our test statistic is simply that coefficient divided by our standard error, if our standard errors are now higher, what's happening to our test statistic? Getting smaller. Which means our p-value is higher, right? So this is the idea from thinking about my test statistic. The p-value is the area to the right of it. Well, if it's a two-tailed test, it's that. This is half my p-value, right? I have another tail on the other side. But if I have a smaller test statistic, that area is going to be larger. So my p-value is higher, which means, is it more or less likely I can reject the null? Yeah, we only reject if that p-value is less than alpha. So we're going to be less likely to reject, right? And we can kind of see this play out in the example we just had, right? So say I look here, my test statistics before were 11.07 and 1.41. Well, they're still pretty close here because out to the decimal, it's going to, oh, why is this not changing? Oh, did my projector shut off again like it did the other class? Why does it do that? I'm gonna do last clap. I just turned it off. So we'll have to wait a few seconds. So what should be the case if I look at those test statistics, they should now be a little bit lower, right? My p-value should be a little bit higher and I'm less likely to reject the null. Now, the example I have isn't a great one in that sense. Like we can kind of talk through the logistics of it, but they're such small p-values, like out to the third decimal, we can't see any difference. They just look like they're zero. But we know, even if that's all we could see from the state output, we know that they have to be larger p-values, even if it's out to the fifth or sixth decimal, right? So let's see if this kicks it back on. It's 14 seconds, then we'll hopefully be back in. There it goes. This starts happening every class period. I might be sending some emails. So, also, why would you have it? Never mind. Set like you have it set the timeout at like 3 a.m. right? Why would you have it set to be the middle of the day? So anyways. So, right, we look at our output. Here's one where it's kind of tough because our test statistic 1.4 went to kind of 3.97 negative. Well, it's actually kind of changing signs here. So we get kind of a weird one where we really can't see, our p-values are basically zero in both scenarios. So this doesn't really allow us to kind of do a whole lot here, right? But we can always think about what would be happening to the p-values based off of this concept. We can think about what's happening to the p-values based off of this concept. Okay. Just a little bit of an aside, kind of going back there. Didn't want to spend too much time on that, but what's one way we can kind of solve this problem? So let's say we think there's some multilinearity going on. We said we could do what? So I've got GDP and a population. I want to still include both of them. Create a new variable, which is just some function of the two. Now, generally, the examples I give just to make it kind of easy is let's just take the ratio, right? So let's take this GDP variable and divide it by the population. Now we still are using both variables, right? The variation exists in both of them, but because we think one is a linear function of the other, we're kind of, I think about this as, I'll come back here, let's say GDP hopefully is a function of population. Well, then when I take GDP, right, I'm dividing it by population, I'm kind of getting rid of that effect, and I'm just kind of left with one value, right? So when I kind of use this ratio, I'm still using the information from both, but now I just got this one variable. I don't have to worry about that imperfect multilinearity. So we're just going to do that kind of moving forward. So I'm going to create this new variable. I'm going to use it in my regressions. So we'll kind of create that variable, run our regression, kind of go from here. Now notice, relative like to before, because and we didn't really talk about this, and I probably wouldn't, I'm not going to expect you to know this or ask this on the exam. But notice how low my R squared was, even when I included both of these. Not only does our standard error impacted by multilinearity, notice what happens to the R squared if I then kind of create this function of the two, right? It was just the ratio. R squared is like 0.34 now. So not only will your statistical significance of your coefficients be impacted, so would your R squared value. So in practice, if we think we have some imperfect multilinearity, we want to try to create a new variable that is some function of those two. So we've done that now. Now let's start adding in some more variables. So I think that there's some variables in the data set which are BMI and schooling, right? So BMI just is like a measure of body mass index. So like the higher it is, well, there's a range, right? If it's too low, you're unhealthy, and if it's too high, you're unhealthy, right? But we have the average BMI of these countries, and then schooling is just the number of average years. So I think like 12 would be the average is like a high school education. Anything above that means that, it's something above a high school education. So we could look at the actual variables here. BMI often is in the 20s, right? We look at schooling, see, some of these countries, relatively low levels. A lot of them are near 12. So we're going to go ahead and kind of use this regression, right? So how would I kind of interpret some of these coefficients? So here, this is kind of a weird one, and I probably wouldn't push you quite this far on the exam. But what would a 1 unit increase in my GDP per capita? Remember, we scale GDP. So this would be for every 1 unit increase. So for every additional $1 billion per person, right? Which just seems kind of like a weird one. But I mean, like I said, GDP is in trillions, right? This would be kind of the expected or predicted change in life expectancy. And that kind of makes sense. If I have more money per person, my economy is probably doing better. My people probably have healthier, better lives, right? They're able to afford more health products. Now BMI in schooling. So here, for every additional year of average schooling that increases in the country, we would predict their life expectancy also goes up by 1.3 years, right? So additional schooling, once again, looks like it's having a pretty positive impact on life expectancies. But what about BMI? So BMI is just measured in points. So for every additional point increase in the average BMI of a country, their predicted life expectancy is actually going up. Well, if BMI gets too high, isn't that actually bad? Shouldn't it have like a negative effect? So let's think about maybe why. So when we run these regressions, let's see here. Let me see if I can remember what the variable was. So there it is. So when I was looking at this, I was predicting life expectancy. And here I'm just going to kind of focus on the BMI variable. But we have those other two variables in there as well. Right? When we see our coefficient estimate, it will include the true effect that BMI is having on life expectancy. But if we left any other important omitted variables out, it's also going to contain that effect as well. So we said, if we have an important omitted variable, the general kind of form that we write this bias in would be the covariance of whatever variable we included with that omitted variable divided by the variance of the variable that we included, and then the effect of that variable that was omitted, what it would have been on life expectancy, or what it would have had, what effect it would have had on the y variable. So here, let's think about, even though GDP kind of captures this, let's think about if we left out like the average income, right? Or maybe the average household income. So I could also think about this as like healthcare expenditures, right? How much money people have to spend on their health. So what's likely true, right? So if I had some measure of income or the amount of money people are spending on healthcare, right? What effect do you think that would have on life expectancies? Having more money, spending more money on healthcare, the effect is likely going to be positive. What would the covariance be between the variable I included, BMI, and income? Wealthier countries tend to be fatter. Yeah, I would actually be like right. It just, that's the way it is. I mean, we look at it, that's the way it is. And so we've got a positive. What about the variance? Variances are always positive. So our bias was positive. So when we saw that positive 1.01 or something like that, it could have been that a large part of that effect that we were seeing, that estimate, was this positive bias. So if we had some measure of income and we included it into our regression, this bias goes away, and now maybe the coefficient we see is actually negative, right? That as you increase the BMI, at some point, it's going to start decreasing that life expectancy. Now, I don't know, it might just reduce how large the positive effect is. I have this variable, it's not perfect, there's no like income, but I have an economic status developed. So let's see what happens if we just add that in. Also, I'm thinking I might have spelled it wrong because it's economy. I was gonna say, because it's not trying to auto. There we go. Economic status developed. Oh, I didn't look in there twice. So I'm now going to run this regression, right? And I would expect if I eliminate some of that positive bias that existed, now that BMI, well, maybe my intuition was a little wrong, right? Maybe that bias was actually negative, right? Now, this isn't like a perfect income measure, so that might be why it didn't really change it the way that we were kind of thinking through the intuition. But as I add in these variables, I'm going to be eliminating some of that bias. Right? I said, I wish we had like an income variable here or healthcare expenditures, but there isn't.
But didn't we also say that if it's too low, it's also a bad thing? So if you have like.
Yeah, so this BMI is not a great example for this exam because after this exam, we'll start to talk about, sometimes we don't just have linear effects. Sometimes we have curvature, right? So initially it might have been increasing, then at some point. So we'll talk more about that after this exam. But that could be partially what's driving this as well. But you know, if you're looking at averages, most of them are like high enough to where we're not really looking at malnourishment BMI values. So we would expect that it's probably negative. But to your point, yeah. Yep. So I guess that variable, I was kind of guessing, I thought maybe it would capture that, but I don't think they have any healthcare expenditure. No. And to this point, I'm kind of simplifying this a little bit, so I'm gonna get rid of this just for kind of what we're doing moving forward. I'm simplifying this a little bit when I'm writing only one bias that exists in our estimates. What truly exists? Well, for every single omitted variable we have, we're actually getting bias in our estimate from every single one of those important omitted variables, right? So if there's other things that are correlated with both life expectancy and BMIs that we're not including in the regression, we're actually also picking up bias from that as well. So the only way we can eliminate that is actually including those variables in our regression. Right? Any questions on this idea before we keep moving? So I'll just tell you, I'm going to ask you to put a sign to a bias, right? Now, I might give you some like correlation, and I might tell you the covariance from some Stata output so that you know what the sign, I'm not just like, you don't have to just come up with your own intuition about what the sign is. But if you have these values, right, these covariances and what the effect actually is if the variable is included, you can always determine what the size of your bias is there, okay? Any other questions on that before keep pushing along here? Yeah.
I guess you answered the question.
Oh, I said a question.
Yeah, ask away. Okay, so for the beta 2 on the equation, that you can find that on Stata output too, just from the coefficient, right?
So this would likely be the way I would ask this question. If I wanted you to put a value to what the size of the bias was, I would do something like, let's see, this is a good question. Let's do, instead, let's say I left off this important variable of alcohol consumption, right? So we could do the same thought experiment where I'm thinking about, okay, if I run this regression and I don't include alcohol consumption, right? I could ask you, so this would be one of two ways I'll ask you. I might give you the original naive regression and say, if I leave out this important omitted variable, what do you think is true about the sign of the bias, right? Or what do you think about the coefficient you see? Is it going to be too high or too low? Well, here, if I think through this one, if I'm leaving out alcohol consumption, what is likely the effect of alcohol consumption if I were to include it in my life expectancy models? I would think it's negative, right? The higher the alcohol consumption of a country, I don't know, red wine maybe is supposed to be good for you, but there's a lot of epidemiology studies that say this should be negative. Now, what would the covariance be between BMI and alcohol consumption? Yeah, right? People that drink a lot, it's a lot of calories, right? We would tend to see kind of higher BMIs. So I would expect the size to be negative. So the estimate I'm seeing is actually going to be too low. It's including this negative bias. So that's one way I could ask you a kind of omitted variable bias question. The other way would be, I might give you the actual regression where you include alcohol consumption and this covariance information. So I say, okay, if you ran a naive regression where you left out alcohol consumption, what would the size of the bias be? Well, the size of the bias would be that coefficient if we had included it, right? So that's our beta 2 in this example. So if I'm just going to do this, actually, I think this will help make the point as well. But I want to make a running total. So we've got what? Oh, stop it. So if we've got negative point, I think it was 0.19 here. No, not 0.19. Negative 0.19.
Didn't you say we wouldn't have that?
So the first way I asked you about the sign, I may just give you the original naive regression.
Right.
I could also give you this output and say, what is the sign of the size of the bias that you would see if you did run a naive regression without alcohol consumption? So kind of going in the opposite direction. So here, I know that that bias that would exist if I didn't include alcohol consumption would be the effect alcohol consumption would have had if I included it. Multiply that by what? Our covariance between that alcohol consumption omitted variable and the variable we were thinking about the estimate of, which was BMI. Well, I've given you that covariance down here. So that's what, 2 point. And then divided by the variance. Well, this covariance matrix, we said that diagonal is telling us the variance, right? The covariance of something with itself is the variance. So here, it's the variance of the variable you included, not the omitted variable, the variance of the variable that you already had included. So this is 4.81. So I get the size of that bias. It is negative about almost 0.1. Now, sure enough, if I would have given this to you. The reason why I wouldn't is because then it becomes easy. What's the sign of the bias if I look at here? If I ran the naive regression, well there, the estimate I see is 1.01. Well, I know that the bias that existed was negative about 0.1. So I should see 1.11 about, right? So where is this at? Or no, what am I? Oh no, I would see sorry, but yeah, it should be a little bit lower, right? Because it was negative. So it should be about 0.01 lower. Now, I'm rounding very egregiously here, which is why it's a little bit off of that 0.1 value. But that's the kind of question I asked. Now, I'm not going to just give you the naive regression and the one where you include, because then all you do is just look at the difference in the coefficients, right? But here, I might do something like this, where I give you the regression with the important omitted variable. I give you the covariance information, and then ask you if you did run that naive regression, what would the size of the bias be? It was actually negative, so we should have been, we should kind of see this estimate be a little bit higher. Okay. Any questions on that?
So yeah, bias is the real regression minus the naive regression. Or is it the other way around? The naive minus the. Right, it's like the coefficient of those.
Yeah, so when we have so when we include the variable of alcohol consumption here,
Yeah.
we've eliminated the bias.
Right.
So this other coefficient would be the actual coefficient plus that bias. Actually, why is this?
So you subtract it to find the size, right? If you gave us the coefficient for both the naive and the included one, you just subtract it, right?
Yeah, but I wouldn't do that.
That would be
Yeah, I'm not gonna make it that, yeah, right, like, so that's what I'm saying, I'll either give you the naive regression, ask you about the sign, or I'd give you this kind of output and ask you about the size, knowing that you can pull out those different statistics from here, okay? Any other questions on that one before I keep moving here? Okay. All right, so I think that's good. Kind of think about, this was our omitted variable discussion. So you'll notice I'll post these after class, but a lot of this is going to be the discussion that we're kind of having, jumping back and forth to the .cam and this file. So we've now thought about omitted variables. The next thing I want to do is think about, and I'm going to steal the code from over here. And I'll let you guys, if you're following along, kind of have some time to kind of write it down. So we're going to use this generate random equals R uniform. We're going to sort it. You don't really have to do that, but just to be complete. And then we're going to generate this small sample variable. So what I'm going to do here is we're starting out with a pretty large data set. So we're looking at some of these p-values. A lot of them are 0. When we have really large sample sizes, we're going to think about what the effect of that would be. We're going to kind of work in the opposite direction to think about, okay, if instead of a large data set, I had a much smaller data set. So here, this is going to generate a sample, a random sample from our data set of size 100. Okay. Now, if you're following along, these are random, so you may get slightly different values than I do. I'm going to just walk through kind of the values that we have here for everybody. This is the code that you would use. The methods of making the decisions of things will stay the same, but you might see slightly different values than I am because you might have a slightly different random sample. Now, on average, across a million different samples, we should all be on average seeing the same values. They're going to be just a little bit different. Okay? So here, I'm going to run that exact same regression that we had before. with just GDP per capita, BMI, and schooling. But for a smaller sample size. So I'm going to add in, I'm only going to want to use the observations that have this small sample variable being equal to 1. So when I run this regression, what's going to happen to my R squared? In theory, if I could take 1,000,000 different samples of size 100 and 1,000,000 different samples of size, what, 2,800? On average, they should have the exact same R squared. Now, any 2 samples, those might be a little bit different, but over 1,000,000 different samples, they would have the exact same R squared. What about the statistical significance of each one of our slope coefficients? Well, I'll show you, I'll pull up the formula sheet just to kind of make sure we all know where it's at, first of all, but also the one that you'll have in the exam. So this standard error is going to be square root sum of y minus predicted y's squared over n minus 2. And actually this changes if we have multiple linear regressions, but for the sake of the kind of question I'd ask you, we'll kind of run with that added formula. The implication will be exactly this thing. So if I'm now taking a smaller sample size, what's happening to my standard errors? If I'm dividing by a smaller number, this fraction will be, if my denominator is larger, what's happening to my test statistic?
Smaller.
If my test statistic is smaller, my p-value will actually be larger and less likely, all right, to reject. So this is like a common theme across a lot of joint significance, individual significance, all these things. The smaller the sample size, the smaller the test statistic, the higher the p-value, the less likely we can reject the null. Right. Now, what is the null here? Just as kind of a reminder, for this individual statistical significance, we're always starting out assuming these slope coefficients are equal to 0, right? That there's no effect. Okay. So, if I run this regression where I'm using a smaller sample, I should expect that all of these test statistics go, yeah, someone's using their finger, down. As a result of my standard errors going up, my p-value should then be larger, right? It might be less likely I can reject. So let's see if I'm full of it here. Oh, because I didn't run this yet. Excuse me. So I generated my random sample of 100. Now notice my R squared 0.6, 0.66. So it will be different. But if I were to kind of repeat this process over and over again, what I'll end up seeing is those average R squareds across the larger and smaller sample end up being the same thing. So on any 2 samples, you know, we're going to see some difference there, but they're going to be pretty close. Right? I then look at my standard errors. So I had what, like 0.008, 0.065. So they're now 0.04 and 0.34. My standard errors are much higher. My test statistics are all lower. Now here, this example, it's not a great one in that I can't actually see what's happening to these p-values because they're still 0. But even if I can't see it, what do I know has to be happening to these p-values? My test statistics are smaller, my p-values have to be going up. Yep. On the exam, probably a little more likely to kind of find a data set or actually see these p-values right down to the 3rd decimal so we can see them change. I just had the thought, I was looking for a data set that had some variables I think could apply to a lot of things we talked about, and this one was one I kind of thought was a good one. So that's the effect if we kind of take a smaller sample. Right? The next thing that I want to think about is, and also just to point this out, because I might ask you like a really easy question here on the exam, but just some of the stuff in this that we might also want to use. How would I find, if I didn't give you the R squared here, how would I find my R squared from this output? So we go to our formula sheet. Hopefully this would help us kind of. Oh, and I have it right there. I might as well just click on it. We have an equation here for R squared. Now, to remember kind of what ESS or RSS, so this was gonna be like our explained sum of squared, or the amount of variation our model explained, total sum of squared, total variation that existed in that y variable. So I'm looking here. The model SS, that's essentially our explained. How much of the variation does our model explain? So all I would do to find my R squared here, take that 7,000, divide it by about 10,000. Right, I'm rounding egregiously here, but just as for the sake of shorthand, right, same shorthand, and that would be reproduce my R squared. Okay.
Wait,
Yeah.
the TSS, is that just the total SS for the column, and then the estimated regression is just the 7,000 given the model.
Yep, so this is the amount of variation my model explains. This is the amount of total variation. So that ratio, that's my R squared. Yep.
That makes.
Any other questions on that one before we keep moving? I am doing things a little bit differently than my other section. I might post both of these even though we're doing similar things, because I think I didn't do this for them. But I think it's maybe a good time to do this. So just to kind of prove this to ourselves, so let's take that 7,000. And let's take that. So this was kind of our explained sum of squares from our model, total sum of squares, right? Let's zoom in a little bit so see what we're doing here. So I could find my R squared by simply taking the ratio of those two. Now, how would I find my adjusted R squared? So our adjusted R squared equation was 1 minus our residual sum of squares over our total sum of squares times n minus 1 times n minus 1 over n minus k minus 1, where this was just the number of variables, the number of independent variables we were including in our regression. So if I remember right, we only kind of started out, I think we had, did I do 3 variables there? Hold on, I'll pull up this on my so I can see. Yeah, so we had GDP per capita, BMI, schooling. So this should be 3. We only have 100 observations now because we're using this smaller data set. Well, now this residual sum of squares was also told to me by Stata. So here, my residual sum of squares is right here. So I'm going to copy this. Now, if I think about, well, let me just put it up here so I can do this side by side comparison. So if I wanted to do my adjusted R squared, that's going to be equal to 1 minus that residual sum of squares divided by my total sum of squares. And then I was multiplying that by what? Well, I had in my numerator n minus 1, so 100 minus 1, divided by n minus k minus 1, so 100 minus 3 minus 1. So this should hopefully give me the exact same adjusted R squared, 0.651, that Stata was giving me. Right? Now, I probably won't like push you as far as like not giving you the adjusted R squared, but if I didn't, you actually had everything you needed here to actually calculate that adjusted R squared, right? Once again, just to, so where's our, oh, do I not have it on here? I'll add that on there. So I'll add in our adjusted R squared equation so you don't have to kind of have that memorized, right? And because we were using that a lot. So a little bit of a side, I hadn't planned on going through that, but we've talked about the adjusted R squared enough to where that could be something that pops up on the exam. Okay. Let's say we have this exact same regression, but I now instead want to do some joint significance testing. Right? So I don't just want to test one individual variable. It's actually, no, there is one more thing I want to do before we move on. It shouldn't be too difficult, but I do want to stress that it's probably something that you all will think is very easy, but I know that it's going to be on the exam, so I want to at least mention it. Okay. So when we're running this regression. I had this GDP per capita, I had BMI, and I had this schooling variable, right? So the values we had here were about, I'm gonna round to the second decimal, 0.15, 1.64, 1.19, and then our constant was 16.40 if we round to the second decimal. So if I asked you to make predictions about life expectancy, right? And I said, okay, for a country, and this is where I have to remember what the average values are. So I'm looking at GDP. So, okay, so somewhere in the, let's say their GDP per capita, a billion per person is 20. Right, so this was kind of their GDP per capita variable. They had an average BMI of 21, and the average years of schooling was, I don't know, 11, right? What would the predicted life expectancy be for this hypothetical country? What do you need to do in this case?
Just multiply and then add.
It's just a linear equation. All you're doing is plugging in those values, right? Each variable, you'll multiply that hypothetical value by the coefficient associated with that value, add them all up. And then the one thing that you don't want to forget, that's very easy to forget, is I also need to add in the intercept always, right? In fact, what would the interpretation of this intercept be?
That everything was 0.
Your life
If everything was equal to 0, so a country with 0 years of average schooling, 0 BMI, and GDP per capita 0, we would expect their life expectancy to be 16.4 years, right? It's weird, right? It's a weird kind of interpretation. That's because we know that for all these variables, we never see 0 GDP or 0 BMI. All the data is way over here, right? But just because the data is up here, our line of best fit, every line mathematically has to have a starting point. Even if we don't see any data points down here at that starting point, it's still like the line still has to start somewhere, right? So we can make interpretations of these intercepts. That's always how they're going to be. When every other variable in the regression is equal to 0, here's the predicted value of y. Okay. Any questions on that? Like I said, it might be kind of it might seem easy, but I know I'll ask you to do something like that. So I feel like it was at least worthwhile to kind of bring it up.
Well, you say you multiply it by the coefficient of each variable.
We get the effect.
Oh, the effect, okay.
Not the effect, right? This will give me the predicted y value, right? Now, each one of these, I guess, if you want to think about it, is like, what was the effect or how much was GDP changing my predicted life expectancy? How much was BMI of this hypothetical country changing that predicted life expectancy, so on and so forth, right? Yep. Any questions on this before we go back? All right, so now we'll think about joint significance, right? So let's say I want to add in, you know what variables I want, I just have to figure out what they're called. So I want infant death. I'm just going to include year. Oh, should be another one. What do I want? Oh, I already used it. So let's say I want to include the year. I think that like as time progresses, countries and like, we go back 100 years, life expectancy as years progress has gotten better and better. We have fewer wars, fewer diseases, things like that. I'm also going to include that alcohol consumption variable. And I'm then going to include this infant deaths variable, right? So it's going to be like I think it's not the number, but it's something like the number of infant deaths per certain number of people. I forget the exact coding of this variable. It doesn't matter for what we're going to do. It's just some measure of the proportion of births or relative to our population, how many infant deaths we're seeing. Well, inherently, if I run this regression, right? What should be happening to my R squared? I've added in more variables, right? So my R squared should be going up, right? I'm seeing people point their fingers up. Now, do you think it's increased a lot or a little? I mean, alcohol consumption in the year might have some influence, but what about this infant deaths? If I'm now controlling for the amount of infant deaths, what would infant deaths do to my life expectancy? Bring it way down, right? So now controlling for that, I'm now kind of thinking about, well, what's the life expectancy in these countries if people kind of make it out of those early years, right? And so I, might expect going into this, my R squared, instead of being 0.66 now, I'm almost at 0.9, right? Because, a lot of what was driving that life expectancy possibly to be lower before was the fact that some countries have a higher proportion of these infant deaths, and those dramatically influence life expectancy. Excuse me. So my R squared has went up quite a bit. So if I'm thinking about wanting to do some type of joint significance testing, we'll have this test statistic that we need to calculate. Now, anytime we have a test statistic, we're thinking about, we take the sample statistic, subtract the assumed true statistic, divide by a standard deviation. If it was for a coefficient, we were always assuming that the true value is 0 divided by standard error. We said we can think about that as a standard deviation. So we're always looking at some sample statistic. We're thinking about this joint significance. What we're trying to test for is whether adding in these variables allowed us to increase the variation we could explain at a statistically significant. We know that as we add in more variables, we know the R squared will be going up, but is it going up at a statistically significant level? So our sample statistic that we're actually looking at is the change in our R squared from the unrestricted model where we included these 3 additional variables compared to the restricted model that didn't. Right? So we know that this difference, if the unrestricted model always has these additional variables in it, this difference will always be positive, which is why we had to use the F distribution, and we're really only doing right tail tests. We said that F distribution has kind of this really long right tail. We use it when we have statistics we know are always going to be a positive change. Not every time we have, but that's often when we see it be used. Okay? We then said we know that as we add in more restrictions, what's going to be happening to that difference? So if I add in more restrictions here, I'm thinking about like starting from my restricted model, maybe another way of thinking about it. If I start adding in more variables into my unrestricted model, that R squared has to just continuously go up. So this difference will be getting larger. So we're going to kind of penalize ourselves for adding in additional variables by dividing by the number of restrictions that we actually had. Right? If I add in 4 more variables, dividing by 4 is going to reduce that value. Right? I'm going to kind of penalize myself for adding in a higher number of restrictions. We then kind of had our denominator was like 1 minus the unrestricted R squared divided by n minus k minus 1. Okay. And this is the last formula in that formula sheet. Now, one thing you can kind of remember, what is k? You'll have that formula sheet, but if you can't remember what k is going to be the number of variables in what? Well, if we can't remember, is it the restricted model or is it the unrestricted model? It's in the denominator with unrestricted, right? So I don't know, that's kind of a, I try to think of test taking techniques. It's not really cheating, but it's a way to remember that it's the number, k is the number of variables in that unrestricted model. So for us, right, I think we had 3 added variables, so our number of restrictions was 3. K, we started out with 3 variables, we added 3 new ones, so our k would have been 6. And we were using that sample size of 100. So if we really wanted to, we could grab the R squared from our restricted and unrestricted model and calculate the test statistic ourselves. That could be something I asked you to do, right? If I gave you the output of both the restricted and the unrestricted model, you could plug in those R squared values. You could figure out, well, what's the number of variables difference between these 2 models? That's my number of restrictions. Plug that in. You'll have your sample size. K is the number of variables in that unrestricted model. Okay. So take a look at that here. Excuse me. So I'll actually go ahead and do this. So I'm going to do my numerator first. So this is going to be my R squared from the unrestricted model, which move this over. Okay. There we go. So my R squared from the unrestricted model is 0.8996. The difference between that and the R squared from my restricted model, right, that didn't include these additional 3 variables. So this is what, 0.6616. I'm then going to divide that by how many additional variables did we add in? Year, alcohol consumption, infant deaths. So 3. Right. What was in my denominator? Well, that was 1 minus my unrestricted R squared. So that was 0.8996. Not times, divided by n minus k minus 1, so 100. How many variables were in my unrestricted model? 1, 2, 3, 4, 5. We don't count the constant. It's just the number of explanatory independent variables. So 6 minus 1. So this was my numerator. This is my denominator. I get an insanely large test statistic here. Now, I can recreate this in Stata. I don't have to do this by hand every single time, right? But kind of knowing what components go into that test statistic will be important for something we're going to talk about here in just a second. What I can do in Stata is just simply use that test command, and then I'm going to test what the joint significance of these 3 variables I added in. So if I run this, hopefully I get that exact same test statistic that we found. Now, there's some rounding errors here, right? Because Stata doesn't have to round to the 4th decimal, and I was, but we get the exact same value. Okay. So for this one, my joint significance, can I say that adding in these variables increased the amount of variation I could explain in life expectancy? And at what levels? So if the yeah.
That's at all levels.
Yeah, it increased that R squared statistically at a statistically significant level. And what levels? Well, my p-value is 0, that's less than everything. Right? So at the 10, 5, and 1% levels. Okay. Now, so any questions before we do the next thing? Because I'm going to complicate a little bit. I don't think we've quite looked at this, but it's taking concepts that we've already talked about. Okay. So what if instead, and let's start, so we got what, another 15 minutes. So what if instead I did this exact same thing, but I'm like, okay, I kind of know what was really driving the R squared to increase a lot there, infant deaths. So let's look at something that maybe might be a little bit more likely or less likely that I can actually reject. So let's say instead I just wanted to do the joint significance of 2 variables. Right? So I'm going to run now this unrestricted model, but instead of year, alcohol consumption, infant deaths, I'm just going to do year alcohol consumption and test the joint significance of those. Okay. So let's think about what this is going to do to my F statistic. I'm going to rewrite it as I talk, and then we'll kind of think through what the impacts are going to be. So if I'm now only looking at 2 variables, what's going to change in this regression? Or in this regression, in this equation? So my number of restrictions is no longer 3, it is now 2. So this is went down. So I have fewer restrictions, so that should do what to my numerator? So that impact is going to be a little bit more likely that I'm going to see a higher test statistic, which means my p-value is going to be smaller, and it's going to be a little bit more likely I reject. Okay? Now, F, I am reducing Q. Inherently, what am I also doing? I'm reducing K by 1 as well. So if this is going down, I'm subtracting a smaller number. So my denominator here is going to be, if I'm dividing by a larger number, what happens to this fraction? If I divide by a smaller number, what's happening to this fraction? So both of these things, by using a fewer number of restrictions, it's going to be more likely I see a statistically significant joint significance test, right? My F statistic will be higher, my p-value will be smaller. However, like many things in economics, if I said, okay, now leaving out that infant deaths variable, am I going to, compared to when I was testing the joint significance of all three, will I then be more likely to find that I can reject the joint significance of these other two? Well, what's also going to be changing? What do you think was driving the gap in between the unrestricted and restricted R squared before? Infant deaths, right? So now this gap that we see in between our restricted and unrestricted model, the year and the alcohol consumption probably not as good at, right? So that gap's probably going to go down, just like many things in economics. The answer is going to be, it depends, right? Because yes, the fact that we have fewer restrictions will increase that test statistic, but we have fewer variables. That unrestricted R squared is now going to be lower, right? So we don't know which one's going to kind of win out. We would actually have to run that test to see. So we go ahead and do that. Okay, well, it must have really been that infant deaths was driving my result, because what's my test statistic now? 0.25. I can't say that these added variables of alcohol consumption year have any statistically significant effect on increasing my R squared, right? They don't explain any more of the variation in that Y variable at any of our statistically significant kind of benchmarks, right? Questions on that? Yeah.
So without those results, if you just asked us conceptually, intuitively, it would be, we can't determine, right? Because just-
Yeah, and I probably wouldn't ask you a question as in-depth as that. But I might ask you something like, assume you found the same R squared. If you reduce the number of restrictions, what impact would that have? Like, I'd ask you about that specific effect,
Right.
not the combination of these two things. Yep. Excuse me. Any other questions before we keep moving here? So one more thing with this joint significance. Let's say, and we'll go back to this example, just no, we'll use this one. I never know what these random numbers are, so I'm always trying to anticipate kind of things. I'm kind of working on the fly today. So let's get rid of this. So I now have a larger sample size. What should that do to my joint significance test? So if I have a larger sample size, and I'll just write it out again here so you're taking notes. You probably don't have always colors. So we want to be able to differentiate between these two different types of examples. So if I have a larger sample size, before we even work through the logistics, we said larger sample sizes should always do what? So I think before we did smaller. If I have smaller sample sizes, we said that did what to our test statistics? Made them lower, which then made our p-value higher, making it less likely, right? So the result was, if I have smaller sample sizes, less likely, larger sample sizes should be more likely we reject the null. So it should be that we're seeing a test statistic. We're more likely to reject the null. It should be higher. So we think about why. If I take a higher sample size, what's happening to this fraction? I'm dividing by a larger value, so the whole fraction would go up, right? Or sorry, no. If I'm dividing by a larger number, what's happening to this fraction? The whole fraction would be going down. If my denominator is now smaller, what's happening to this fraction? Dividing by a smaller number, my test statistic is going to go up. That means my p-value is going down, which means I'm more likely to reject when those sample sizes are higher. So higher sample sizes are always going to make it easier or more likely we can reject. Smaller sample sizes, less likely. And this is kind of the mechanism through what, how it does it. So if we run this regression, we might see that before where we couldn't reject at any level. right? P-value is 0.77. Now, if I use the entire sample, now I get a test statistic that's a lot higher because I went from 100 to 2,800 observations, right? And so this kind of stresses the importance of having large sample sizes. The more data, the better. Okay? What are questions there before we keep moving?
You said that. Can you explain the prod greater than F, meaning that the 0.0000 statistic and how that explains.
So all this is, excuse me, it's just like over here.
Right,
That's just our p-value.
oh, and because 0 equals.
Exactly. Yep. Yeah, these joint significant tests, it looks a little bit different in terms of the format. Because we're not dealing with a test statistic now, we're dealing with a T statistic now, we're dealing with an F statistic. So this is just gonna tell us, here's your test statistic, here's your corresponding p-value. Yep. Any other questions on that before we keep moving? Okay. Save that for next class or not. Got 10 minutes. I think we can do this quickly. Let's see. Let's go back to, so. Let's do our original 3 regressions, or sorry, 3 variables, so just up to schooling. I'm now going to want to include, so there's this region, so it's got like all these different regions. I'm going to include indicators for each one of them, right? So here, I'm going to encode, is it capitalized? No, that region variable. I'm then going to generate kind of a new variable that I'm going to call region reg, right? So what this will do is it assigns a number to every one of those regions. So if I go here now, this variable I created, European Union is 4, Middle East is 5, Asia is 2, Central America is 3, so on and so forth. So I now have a variable that I can very quickly include a dummy variable for every single region. So this I command, so I'm going to do region reg, will create dummy variables for every single region that these countries could be in, right? So if I included all of them in my regression, what am I going to have? I'm going to have to omit one because if I don't, I'm going to have perfect multicollinearity, right? This is the idea that, you know, if I know 6 of the values, I automatically know the 7th, or however many regions there are, right? So Stata will choose one of those to kick out. Problem is, it doesn't really tell us which one it is, right? So I'd have to kind of go through here, okay, look, all right, which one is it going to leave out? And I'd have to figure out what was it. I'm going to guess it's rest of Europe. No, rest of Europe's in there. This is only downfall of the I command. So let's see if I can figure out. So rest of Europe. Is Africa not in there? Yeah, so Africa was the one that left out, which means all of these coefficients are the predicted change in life expectancy relative to that group that they left out. So relative to Africa, every other group here, right? If your country is in this region, all of these coefficients are actually positive, which tells us what? Africa has the lowest life expectancy, right? Now, if I wanted to pick and choose which ones I left out, let's say I look at this and I left out the European Union. What would all of my coefficients now become? Yeah, if I leave out, notice, well, what's the one that has the highest predicted life expectancy? That would just be the one that has the highest coefficient. That's the European Union. So if I leave out the highest, all of my other coefficients for every other region will now become negative. What if I wanted to know the difference between, Asia and the rest of Europe? If I want to know the difference in the predicted life expectancy between Asia and the rest of Europe, without running another regression, what do I need to do? Simply subtract their coefficients, right? So Asia would expect on average about what, 0.5 additional years of expected life. Holding everything else in this regression column. I need to be careful as I'm making those interpretations.
Those like just regress together, right?
Regress what together?
Like the two, like the difference between data here.
Yeah, if I wanted to do a different way, instead of subtracting those coefficients, what's another regression I could run where I just get one value that tells me that difference? So remember, these coefficients are always the effect of being in this group relative to the group I leave out. So if I want to know the predicted difference between Asia and the rest of Europe, kick one of them out. Now I'll have one coefficient. If I kick out the rest of Europe, the Asia coefficient tells me the additional life expectancy relative to the rest of Europe. If I leave out Asia, the rest of Europe's coefficient tells me the expected difference in life expectancy between Asia, that group I left out. Probably, you know, it's hard to know without looking at the results already. It probably would make the most sense to leave out the rest of Europe just because Asia would be a little bit higher, so we're dealing with positive values, but we could do it either way.
Some of the coefficients were negative and some were positive, but that means that the one you left out was somewhere in the middle.
Yep. Yeah, if we had positive, and that would be a case in which, like, honestly, we just kind of lucked out that the default here ended up being the lowest group. That's not always the case. The one that it chooses to leave out. Like I said, I thought, well, that can't be the case. I might just have had less. I might have had less. Let's see. So what was that? I called it region reg. So yeah, it left out the group that had the highest number of observations. So it didn't matter that it was the lowest. Like I said, I'm pretty sure this is the procedure it uses unless you like go in and there's a way to like add in things to tell it not to do, like to leave out the lowest but yeah, it chooses generally the base comparison group. It wants to be the one that has the highest number of observations. So in our example here, that would just be the group for Africa. That's why I kicked it out. But if we did have positive and negative values, that would tell us that the group that was left out was somewhere in the middle. Yeah. Other questions? This before we go.
Just to choose how to leave out one, you just don't put it in the regression, right? When you write, that's how you choose.
Yeah, if we use the shortcut of IDOT, Stata chooses for us. But ultimately, like if we're doing this by hand, we could create dummy variables for every single one of these regions, throw them all in, and then choose which one we want to leave out. Which one's better practice? Honestly, it's just a pain to have like, well, however many variables we have here to always going to have in looking at. So generally people use this IDOT command. And then it doesn't really matter which one gets left out technically, because we can always make comparisons just using the coefficients between any two of these regions. Yep. Or any two of these groups. Other questions? All right. So just kind of a little bit of a feedback. We went through a lot of stuff here, but is this helpful at all to kind of see how we see data kind of bouncing back and forth to the formulas? Okay, I know like this isn't like the format of the exam, but I think that this will be, I think this is beneficial. I hope, hopefully it was, you felt like it was. I think that seeing this today will be very beneficial for all of you who are here. Like I said, Tuesday will probably look a little bit more like what you see in other classes where like we'll work through problems with this practice exam just to kind of familiarize yourself like with like more of the format of the actual questions we'll see. I think I really wanted to set us up today. I think this will help solidify some of the concepts of what we're doing. Okay. Other than that, don't forget about that quiz. And then tomorrow, problem set by next Tuesday. Have a fun, safe fall break, and I will see you guys on Tuesday.